I think we all kind of have an appreciation for the definition of dimensional analysis. This is a simple conversion from one dimensional level to another, whether it be intra-dimensional conversion, that means English in English, pounds to ounces or something, or interdimensional conversions, which would be, say, English to metric. And so we'll probably be using metric more times, intra-dimensional conversions in the SI system than any of the others. So anyway, in dimensional analysis, I divide these for academic instruction into three areas, three types of conversions. One I call simple conversions. Two, multiple conversions. And three, complex conversions. Now, if we're talking about a simple conversion, that's a unit-to-unit conversion. Grams to pounds or pounds to grams. So we don't have any crossovers like that. Multiple conversions are squares and cube conversions. And complex conversions are when the unit system is a combination of fundamental quantities, like pounds and miles and pounds. You can't convert miles into pounds or pounds back into miles. So this is units with different fundamental units. And I'll go through an example of each one of these, and I think you'll appreciate the simplicity of it all anyway. Most people that come to the course are well versed in these dimensional evaluations anyway. Simple conversions, that's unit to unit. And in context, we'll just make up a problem that we're given. Say you're given age of young student to be 21 years old. How old is student in seconds? So you, whatever your age is, convert to how old are you in seconds. So in instructing this, I tell students, start with identifying the question in the problem and set that equal to some known quantity in the problem. So given the age to be 21 years old, and your object is to go to seconds, so you got 21 years and some unknown in seconds. So I simply set it up, how many seconds equal 21 years? And then the idea is to take that dimension, 21 years, and convert it into seconds. So I think that's a pretty straightforward. Everybody okay? Stop me if you need to certainly ask questions. Now I want to get rid of the years. Actually, this is actually over 1, so you, as a sidebar there, I want to get rid of years, so to speak, and I want to go to seconds. Well, I don't know the equivalent relationship between years and seconds, okay? But I do know years and days. So I'm going to come here and go years and days. So 1 year is, say, I'm going to say 365 days in a year. You can look it up look it up in the conversion table. Now that would, of course, get rid of the years. Now we're in days. So then you want to go to days. I can go to hours. So you look up days and hours, 24 hours in 1 day. Now when you set these up, be sure the number conforms to, associates with the proper dimension. You don't want to have the entry 1 hour is 24 days. Now, so be careful about where you put your numbers. It has happened, trust me. Okay, so you get 24 hours in a day. And then we continue that. We've gotten rid of days now. We're in hours. So we can go hours. Now, I do know the seconds hour relationship. There's 3,600 seconds in an hour, and so I can cancel that out. And the idea is 60 times 60 is 3,600. And so punch that into my calculator and set this up. 21 times 365 times 24 times 3,600 all over 1, and it's all in seconds. So 1 times 1 times 1 and so forth, like that. So, okay, that's the calculator answer. How should we report this answer in terms of significant figures? The conversion factors, do not use those to define the significant figures. You must use data that's given in the problem based on the experimental observations. So in the problem itself that I've given you, it only has 2 significant figures. So based on that, we should convert this to, or round it, to 2 significant figures, which would mean this would be 660,000,000 seconds, 2 sig figs. Everybody good on that? All right. Of course, there's no decimal specified, so that would be 66. Now, one good little reference to this is what's the distance from the Earth to the Sun? I think the common understanding is 93 million miles. Okay, so it's 93 and then 6 zeros. And no decimal, so it's 2 sig figs. That doesn't mean the zeros are not important, but that you have to keep those for dimensional consideration. So that's a simple conversion. Okay, multiple conversions are just like simple conversions, except what you want to do is solve as a simple conversion, then square or cube conversions factors. And that's your procedure. So, given a problem,
Read it out loud because your handwriting is a little
Small. Is that centimeter squared?
the area is given to be 3.8 times 10 to the, I'll clean it up, 3.8 times 10 to the 4th centimeters squared.
Thank you.
Not a volume. Volume would be cubed. So you're either squared or cubed. That's all. Everybody okay on that? What is the area in square feet? question?
No.
You good? Okay. So in the same context, we want to identify the question and then relate it to some given data. And of course, that would be the 3.8 times 10 to the 4. I'm making up the numbers. Is common. Okay, so how many square feet is equal to 3.8 times 10 to the 4th centimeters squared? And then we apply the simple conversion of centimeters to feet. Okay, so I want to remove centimeters, and I happen to know, you can look on the conversion sheet, I know the relationship between inches and centimeters is 2.54 centimeters per inch, and, well, I'm running out of room, times, okay, that'll get rid of the, and then inches goes to feet, and I have 12 inches, of course, in 1 foot. Now, once I get to the value that I'm looking for, a dimension I'm looking for, then I go back and square each of the units and then write the computation from there. Do not square the given data because it's already given as a square. Okay, so you don't want to double square the stuff that's already been squared. Now, that means centimeters will cancel, inches will cancel, and at the end of this, you'll have square feet. I'll just bring that back down here then. So we have 3.8. Let me do it this way. Neater. So we'll have 3.8 times 10 to the 4th up here, divided by 2.54, and that's divided by 12. And we're in square feet. Squares in here and here. Big nasty looking number off the calculator. And I just copied it right off of that. Anyway, use the coefficient of the given data to define your sig figs. In this case, it would be 2. So this would round to 2. Now, since 9 is greater than 5, we want to increase 0 to a 1, and so that'd be 41 square feet. Appropriate answer. Okay. So the biggest learning element here is squaring the conversion factors and then applying the dimensional conversion. Let's say you're given density CO2. Given the density of CO2 is 2.3156 grams per cubic centimeter. What is density in pounds per cubic foot? There we go. So as in the first two types of conversions, we identify the problem, which is pounds per cubic foot, and we want to relate that by an equal to given data, 2.315 cubic meters. Let's put that cubic meters in grams per cubic. Boy, that's way heavier than it should be. 2.3156 grams per cubic meter. Like that. And so we'll first convert the grams to pounds, and this would be grams and pounds, and I happen to know there are 454 grams and 1 pound. So that allows us to convert to the needed dimension of pounds. Now, going to feet, now we start a new set of conversion factors. But notice it's on the denominator side. So to get rid of the feet, we put it as a numerator now, like that. And if we're going to, I'm thinking centimeters. We're going to go to, well, I need to get this one straight too. Senior moment, okay. Okay, so we have meters going to feet. And so I want to get rid of my meters. I can go to centimeters. I can go through inches and stuff. So there are 100 centimeters in a meter, and then we'll go centimeters to inches, 2.54 centimeters an inch, and then 12 inches in 1 foot. Now go back and we want cubics values, cube and cube. Then you set up your map. So I've taken all the numerator values and then the denominator values, put them in the mathematical ratios shown, and then we'll run out the calculator answer, and then we'll round it. And of course I got 1, 2, 3, 4, 5 significant figures in the data given, and so whatever the final answer in pounds per cubic foot needs to be, the calculator answer needs to be rounded to 5 sig figs. I got 0.0014428 pounds per cubic feet. The answer I got. Y'all back me up on this if you would. Okay. Now, of course, the 5 sig figs, we count this way, it'd be 1, 2, 3, 4, 5. So we've got to retain through the 2. And so since 8 is a 5 or greater, and we're going to drop the 8, the first digit you drop is 5 or better, then the last unit digit retained has to be increased. And so that is equal to, well, put it in here, 0.00014443 pounds per cubic feet. And then in exponential notation, we will need to move 4 places, a -4. So that'll be 1.4443 times 10 to the -4 pounds per cubic feet, like that. So I want to begin by defining percentage and then saying something about what you should think about when you see a percent in a chemistry problem or whatever kind of problem you see it in. Percent, by definition, is part over total times 100%. Now, I'm telling you nothing you may already don't know. But the thing I want to emphasize, this part over total, without the 100 in there, is what we call the fractional quantity. The percent only comes from the multiplying by 100 and putting this little symbol on it. Well, what does that mean? This simply means parts per 100, or hundredweight is what most people will say. So let's say you're given a solution, SOLN, you'll see me abbreviate a lot of things, a solution that is 15% in sodium chloride, okay? And then it asks another, blah, blah, blah. That's just part of the data. So when you see 15% in sodium chloride, what should your brain say? It should say 15 grams NaCl over the total. What's the total? Well, that's 100 grams of solution. So when we're talking about percentages, you need to translate that into parts per hundredweight is the way you should think about it. And in that context, it instantly gives you a conversion factor, which simply means you have 15 grams of sodium chloride is equal to 100 grams of solution. And that is a conversion factor just like inches, 12 inches equal 1 foot, except that you're working the problem in grams of sodium chloride and grams of solution. So, to show you how this is applied once you use it, calculate the mass of NaCl in a solution, an aqueous solution, that is 12.5 weight percent. Now these are weight percents. Weight percent sodium chloride. Mass sodium Na. 750 gram. I forgot that. In a 750 gram solution, that is 12.5% sodium chloride. Now, we all know how to just move the decimal over 2 places, and then mass in grams equals 0.125 times 750, and we hang a grams on it. But that's not always going to be as easy as that in some of the problems, and we'll work them in the future to emphasize them. But what you should do is how many grams of NaCl is equal to something in that system. Well, you've given 750 grams of solution. So you need to get rid of the dimension grams of solution. It's like 750 inches, and you want to go to feet. So just what I showed you earlier, this now becomes a simple conversion. And so you want grams of solution down here and grams of NaCl in your conversion factor. So that's where you are at the grams of solution, and you want to go to the grams of sodium chloride. So what are the numbers that go in here? Well, you're given a 12.5. And what I was trying to explain to you is that when you see this, you have to realize that it is 12.5 grams per 100 grams of solution, whether they tell you or not. And so then grams of solution is the dimension that will cancel, and your answer will be 750 times 12.5 divided by 100 grams sodium chloride. So the percentage number, 12.5%, is converted into a conversion factor that solves the given. So you convert your percent to something that will get rid of, if you will, the given. So you've got a given over here, so what does it tell you to do? Well, I've got to have grams of solution, and what does this tell me? So I've got to have 12.5 grams in so much solution. So that's what I'm trying to tell you, is that when you see just the percentage right there, you take that number divided by 100, and you tag it on to whatever the bulk sample is. Here we're talking about solution is your mixture. That's another way to look at percentages. You're looking at part of a mix. That's part over total times 100. That part is the 12.5. What's the total? It's the mix. That's your 100 grams of solution. Next is parts per million. Many of you have seen this. ppm is the abbreviation for it. And what you need to learn here is how to convert a percentage into a parts per million, or parts per billion, which we'll use a second example. Okay. So we're given concentration of element X is 0.000315% by weight in atmosphere. What is this concentration in parts per million? Basically, is how many parts per million equals whatever this 0.000315% is. Okay? Well, what does this mean? Well, this 0.000315%, and you'll see sometimes people will write W/W means that it's weight ratio part over total, element X over the total atmospheric weight or whatever. Okay. What does it mean? It's parts per hundred, 0.000315 parts of X. That's what that is, what it says. Over 100 parts atmosphere. That's what it means. Now, if you want to go to parts per million in this, everybody understand what I just did here? Do you understand what I did?
Yeah.
You sure? So when you have a percent to a parts per million, you can set this much up. The rest of it's easy because all you got to do is 10 to the 6. And that's ppm. Just multiply it times a million. And so that would be 0.000315 times 10 to the 6 over 10 squared parts per million. And that cancels to 10 to the 4th. And then we'll move this to right there, 10 to the minus 4. So that'd be 3.15 parts per million when everything's said and done. And you can punch all that in your calculator if you want to. That's the same thing. If you're interpreting percentage and then multiplying times a million. Okay? Same thing with parts per billion. ppb. If you're given percent to parts per billion, multiply by 10 to the 9th. That is, whatever that percentage is, when you express that percentage, just simply multiply it times 10 to the 9th and then put the new units, parts per billion, on it. Now, what if you're given parts per million or parts per billion and you need to go back the other way? Well, essentially, what are you doing? You're converting to parts per hundredweight, pph. So you would multiply by 100. But you have to interpret your given. Say you're given a concentration to equal 32.75 parts per billion equals how much in a percentage? You're going to convert that billion to parts per billion into a percentage. How would you go about doing it? Well, it's pretty straightforward. Percent, well, first you have to interpret what parts per billion is. Well, that's 32.75 parts X, whatever it is, that's because the assumptions has got to be the part, over 10 to the 9th parts total mix. Like that. Now, that's the interpretation of whatever data you're given. So if you're going to a percentage, you multiply times 100 and put a percent on it. And so you take yourself back to the percentage. So it's really a simple conversion. If you understand what is meant by percentage, parts per hundredweight, parts per million is part of X over 10 to the 6th, and parts per billion is parts of whatever substance it is, 10 to the 9th. This is parts of X over 100, or 10 squared. So in your conversions, it depends on where you want to go. You take that part per 100 times 10 to the 6th, and that'll give you parts per million, or times 10 to the 9th to give you parts per billion weight, like that. You see what I'm doing? I'm just taking the term, the data given in percentage, and multiplying it times whatever I want to go. And so here, if you want to go to percentage, is times, let me do this. If you want to go to percent, this one is times 10 squared, and if you want to, and then hang it with a percentage, times 10 squared, and percent. I can't get it any simpler. I mean, it's no more complicated than that. And of course, the X factor in here is, of course, whatever you're studying. And all you're doing is expressing it in different terms. Instead of working with 0.0000123 all the time in a percentage, it'd probably be a lot easier to work in parts per million or parts per billion, because you kind of have, say, 1.23 parts per million or something. And that's just, I don't know, it's just a simplicity thing. We all know what the issue is in temperatures. I mean, we have degrees Fahrenheit, degrees Celsius, and Kelvin. Kelvin doesn't have a little degree mark on it, so don't put it circle on it. We'll talk about that when we get to kinetic collective theory. Anyway, the idea is to convert from Fahrenheit to Celsius and Celsius back to Fahrenheit, or Celsius back to Fahrenheit. Well, what are the formulas for that? Or now, in going to Kelvin, which you will need a lot, it's degrees C going to Kelvin temperature, or Kelvin back to C. So if you're given Fahrenheit, you have to calculate C before you go to the Kelvin. Okay, so for the first conversion, degrees Fahrenheit from given degrees Celsius is 9/5 degrees C plus 32. Now, and this gives you from Fahrenheit, gives you Celsius to Fahrenheit. So you're given Celsius, go to Fahrenheit. Degrees C is 5/9 degrees F minus 32, but you got to put the F and 32 in parentheses, like that. So given Fahrenheit, you can go to Celsius using that formula. Or if you want Kelvin, it's degrees C plus 273. So there are the three pragmatic learning formulas to make your temperature conversions. Now the question is, where do those formulas come from? And I'm going to show you where they come from. Now, so you won't have to derive these formulas. Just learn these, and a lot of times people's calculators have the conversions on them, but you need to know how to do them anyway. Temperature conversion formulas. So what you need is an XY graph, like this. And on the x-axis, we're going to call that degrees C, and on the vertical axis is degrees Fahrenheit. Now, we're going to plot on this graph the freezing point of water and the boiling point of water in Celsius and Fahrenheit. And so this starts at 0 and goes up to, say, 100. And this starts at 10, 20, 32 Fahrenheit, and not to scale, 212 Fahrenheit. Okay, so these are pretty commonly known dimensions for boiling point and freezing point of water at standard atmospheric pressure. So this point right here is Celsius, is 0 degrees Celsius and 100 degrees Fahrenheit. 32 degrees Fahrenheit. The point here is 100 degrees Celsius and 212 degrees Fahrenheit. And so we get a little line between these two, and that allows us to apply the point slope method and solve for Fahrenheit in one case and solve for Celsius in the other. Move it up just a bit. The point slope expression is y minus y prime equals delta y over delta x, x minus x prime. Now that's the formula you should have learned in algebra class on point slope analysis. Well, when we translate this into Celsius and Fahrenheit, we have degrees Fahrenheit minus whatever you choose in here. I'm going to use the freezing point in here. So that would be Fahrenheit freezing point, 32 degrees Fahrenheit. Well, I better bring this down so you won't make a big mess. Degrees Fahrenheit minus y, 32 degrees Fahrenheit. Now the slope is changing y, so that'd be 212 minus, you don't even have to put the units in, just put 32. 212 minus 32 over 100 minus 0, so that's changing y over changing x. And then you have degrees C minus 0 right there on the end of that. So when you simplify this, you have degrees Fahrenheit minus 32 equals 212 minus 32, I think it's 180. 180 over 100 degrees C. Now, looking at this last expression, just solve for degrees Fahrenheit and then solve for degrees Celsius. And you'll get those formulas that I just wrote down for you. And you look at this, just what would you do here? And simplify this. Of course, this goes to 9/5 if you look at it. So that's the whole, what I'm trying to show you. So you would add 32 to both sides of this and solve for Fahrenheit, and you would get 9/5 degrees C plus 32. And down here, solve for degrees Celsius, you would get degrees Celsius. See, that's why you see you have to put, divide both sides by 9/5, so it becomes 5/9, but this winds up in parentheses, and so that is 5/9 degrees F minus 32. Now you play with it if you want to. But I always show this class that I teach this to, where these come from, because I don't know that anybody's ever seen that. And it's a very simple derivation if you understand the point slope application. Okay, so energy fundamentally is the capacity to do work. And fundamentally, work, our physics friends tell us, is force times applied to an object and how far that object moves, distance. Well, if we apply the standard international units to these dimensions, fundamental quantities here, what we find work in this context is force is second law of Newton is mass times acceleration times distance. So putting in the units, we have kilograms for mass. Acceleration is meters per second squared. I should ask me. Second squared, and distance again is meters. So when we combine these units from the definition of energy work, we have kilogram meters squared over second squared. Of course, this is obviously a complex unit for work and energy. That's the unit for work and energy. So to simplify this, the scientific community has redefined kilogram meter squared over second squared and call it a joule. And that's where that particular energy unit comes from. Now, there's a second, and I'll show you the relationship, which is what I'm going to, is the conversion factor between joules and the calorie, what we call the scientific calorie. Lowercase c is typically the, this one's usually lowercase j, or it depends on who's writing the note. We're talking about a scientific calorie, not a nutritional calorie. Nutritional calories are defined as 1,000 scientific calories, or 1 kilocalorie scientific. But so what we work with in this course and reactions and stuff, if you make a conversion to calories, it is defined as a scientific calorie. The 1 calorie, by definition, established by the International Union of Pure and Applied Sciences, chemistry, standard weights and measures, yada, 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 is defined as the following. The amount of heat needed to raise temperature of 1.000 gram of pure water by 1.000 degree centigrade. That's the absolute. And that's also called the specific heat of water, and has C equals 1.000 calories per gram degree C is the way that is typically listed. So we have 2 energy units that we typically have to deal with and in our course right here, and that's joules and scientific calories. And what I'm trying to get to in all of these notations is 1 calorie, scientific calorie, is simply equal to 4.184 scientific joules. Now you'll have expressions in kilojoules, you'll have expressions in kilocalories, and going back and forth. But this is the conversion factor that's typically used in making conversions between those two types of energy numbers or energy units. My objective here, of course, you will need to have an understanding of the definitions more than anything. So what I've done is shown you where it is, but in a practical context, that's about all you're going to use is applying this conversion factor. Now, I don't have to work a problem because it's a simple conversion. You're going from joules to calories. And so you're given a data that says 213 joules goes to equals how many calories. So you apply that in that format.